And yes, we have John Jamieson with us today. So John is an associate professor and the Canada Research Chair in Marine Geology at the Memorial University of Newfoundland. So his research program focuses on submarine hydrothermal systems and the formation of deep sea mineral deposits. And having participated in over 20 research expeditions in regions ranging from the South Pacific to the Arctic Ocean and the Mediterranean, it is going to be awesome learning from him today about exploring for massive sulfide deposits at the bottom of the ocean. So it's going to be a really, really good session. I hope you all enjoy it. And thank you so much, John, for joining us today. It's amazing having you here.
Thank you for having me.
Before we do get stuck into your presentation, I was wanting to know what got you into geology in the first place.
Wow. I would have to say probably the right teachers at the right time in school. I had some really great science teachers early on, and I think that's it. Just really good teachers, teachers who took us out of the classroom. That was a big thing, and it just stuck.
I love that. That's really cool. And you have gone far and wide with your role. What have been some real standouts, in your career journey so far?
Oh well, I mean, I started out in mineral exploration on land, and so that took me up to the Canadian Arctic, which is just a fascinating place. The people, the land, the geology, of course. But now all of my all of my field work, if we can call it that, is at sea. I spent probably close to 2 years on research vessels. And highlights got to be going down to the bottom of the ocean in a submersible, and seeing black smokers up close. It's pretty hard to beat that.
Wow, that's incredible. Um, and I believe that you did bring some really cool pet rocks with you today.
I did.
I cannot wait to hear about them. Can you give us a little show?
Right. So I got a couple of pieces of, let me get in the camera here, black smoker samples. Get my phone out and put
Can
some
you?
light on this so you guys can see. Um, So this is a piece of a black smoker from the Endeavour Vent Fields, which is off the west coast of Canada. It's from about 2,200 meters depth. You can see the conduit there. It's lined with
Hi.
chalcopyrite in there. Um, I have another sample here of a black smoker. This is a tiny piece from the near the Galapagos Islands.
Oh,
And this
wow.
one is there's an interior conduit here, and it's coated in sphalerite, so a lower temperature mineralization. And my third sample, at the opposite end of the coolness spectrum, is a manganese nodule. So this is from the Atlantic, but these, of course, are in the news a lot for the possibility of mining these from the Pacific Ocean mostly. But anyway, cobalt and nickel rich manganese nodule.
Wow. They were cool. Thanks for showing us them. That was really, really awesome. But yeah, thank you so much again for joining. I'm so grateful that you're here, and it is so late there, so even more grateful. If you want to share your screen, and we can get stuck into it. So thank you.
Okay, right. So exploration for massive sulfide deposits at the bottom of the ocean. I'm going to take you on a bit of a visual journey to the bottom of the ocean. Figure out how to use PowerPoint. Right. This is a black smoker, the bottom of the ocean, forming on a mound, which is in the initial stages of formation of a massive sulfide deposit. So we are on the Mid-Atlantic Ridge here. This is a site called Irinaskoye. It's over 2.7 kilometers deep. And all the rocks you see there, it's all massive sulfide debris. And the fluid coming out of the that black smoker chimney there is about 360 degrees Celsius. And all the black smoke are tiny particles of sulfide minerals that precipitate when hot hydrothermal fluid mixes with cold seawater. So this is your classic sort of ore forming environment for volcanogenic massive sulfide deposits, VMS deposits. These black smokers come in a variety of flavors and sizes and temperatures. Sometimes it's very smoky fluid, sometimes it's very clear fluid. It really depends on tectonic environment. It depends on depth. There's lots of animals that grow on these black smokers. There's a lot of microbes that grow on these black smokers. All that fuzziness you see there, that's all microbiology. There are worms, there are mussels. So these things are not just geological features on the seafloor, but also biological, ecological features on the seafloor. They're your classic tube worms. Most of the organisms we see at hydrothermal vents don't live anywhere else. They are associated only with hydrothermal vents. All that white material you see there, that's all bacteria. So, it's easy to see why you can get so attracted to studying these systems. They are just fascinating processes at the bottom of the ocean. Briefly, what is a hydrothermal system? Well, it's circulation of seawater through oceanic crust. The two ingredients you need is a shallow heat source, some sort of magmatic heat source, and you need permeability in the crust. And where do you get those? Tectonic plate boundaries, so mid-ocean ridges, volcanic arcs associated with subduction zones and back arcs. You have heat, you have faulting and fractures of the rock. That drives the circulation of fluid. Cold water infiltrates into the crust. It heats up, it reacts with the host rock, and in doing so, strips things like metals and sulfur out of oceanic crust, transports that all up to the surface, and when it hits the sea floor, again, the hot hydrothermal fluid mixes with cold water and causes the precipitation of sulfide, sulfate minerals, and you form these black smokers and you form chimneys and mounds on the seafloor. Now, why? Why would we want to study these? There's actually many reasons why hydrothermal vents and hydrothermal circulation is important. One of them, heat transfer. This is a mechanism for cooling hot oceanic crust. And so studying focused high temperature hydrothermal systems like this allows us to understand the thermal profile of oceanic crust and heat transfer from the earth to the oceans and ultimately out into space. So heat transfer is one. Elemental fluxes is another one. So we have not only material being transported by the hydrothermal fluid up into the oceans. This therefore affects things like ocean chemistry and sedimentary deposition in the deep water. But also it removes chemicals that are dissolved in seawater into the crust. Things like magnesium and sulfate, which are dissolved in seawater, get trapped in the crust during the circulation. So there's flux into the ocean and a flux out of the ocean from hydrothermal circulation. Deep sea ecology, we saw already some of the animals that live on these hydrothermal vents. You can see in the video in front of us now. There's some shrimp. These are shrimp that are endemic to hydrothermal vents. And I see some crabs in there and some gastropods. So these ecosystems are very unique. They're the first discovery of chemosynthetic hydrothermal or chemosynthetic ecosystems that rely on the energy from the hydrothermal fluids as opposed to sunlight. And then finally, this is a mineralizing ore forming system. These are ore forming fluids. These hydrothermal systems produce massive sulfide deposits on the seafloor that have been preserved in the rock record as VMS deposits, volcanogenic massive sulfide deposits, which we've been mining for thousands of years. And more recently, there is actually a growing interest in mining these deposits directly off or directly on the seafloor today. And this is what a lot of my research focuses on. Is that possible? How would we do that? What are the environmental effects of doing that? What are the economic factors that go into this, regulatory factors? This is a brand new field for which we know extremely little, which I hope I will get that point across in this talk today. So the talk today is going to focus on how do we find these hydrothermal vent fields on the seafloor. So here's a map of the oceans. You can see all these yellow triangles. There are about just over 400 of them. These are the sites of the known high temperature vent fields that have been discovered to date. So over 400 of them. You can see there's this clear association of the location of these vent fields with major tectonic boundaries, like mid-ocean ridges. The Mid-Atlantic Ridge is a good example. And if you look on the right of the screen, we have the subduction-related environments with volcanic arcs and back arcs. And there are a few interesting things to notice in terms of the distribution of these triangles on this map. You can see areas, for example, the East Pacific Rise to the west of South America, where there are a lot of triangles closely spaced. And you can see other regions where there are few triangles. And if you look in the southern Pacific Ocean or south of Australia, you can see there are mid-ocean ridges with no triangles on them. And is that because there are no hydrothermal systems there? Absolutely not. It's simply no one has looked there. No one in the right mind wants to go to the Southern Ocean because you'd be vomiting over the side because of the terrible weather the entire time. In my mind, this map is not a map of the distribution of hydrothermal vents on today's ocean. It is a map of where we've looked for hydrothermal vents on the ocean. There are much more to be found. We've done some initial calculations where we predicted that there's probably about 1,000 active vent fields on the seafloor. That number is certainly a minimum. There's probably much more than that. Every time we go down, even to well-explored areas, we keep finding more and more. Okay, so how do we find all these vent fields on the seafloor? Really, we start with a map, just like we would on land. Any sort of geology, you start with a map. So here is a bathymetric map. It's a map of the depths topography of the seafloor at a global scale. Where does this map come from? So this is a global map of the ocean, and it actually comes from satellite data. It comes from satellite altimetry. And the way it works is we have satellites that bounce radar off the surface of the Earth, and you can measure topography from that. And you can do that over the oceans. Now, why would you do that over the oceans? Because they're flat. And you do it because the oceans are not flat. The topography of the seafloor is mimicked in the topography at the sea surface. And that's what this little cartoon shows us. If you have a seamount, some sort of underwater mountain or ridge, volcano, there's more material there. There's a greater gravitational pull, and therefore water is attracted to that area, and it actually builds up over that mountain or ridge or whatever positive feature. Likewise, an oceanic trench There's less material there because it's water instead of rock, and you have less gravitational pull. And so the sea surface acts as a proxy for the topography of the seafloor. A kilometer high volcano would probably result in a sort of meter elevation gain at the sea surface. So it's not something you can discern with your eye, but with satellite radar measurements over and over again, you can subtract the effects of the tides and the effects of waves, and you can turn that into this global map that we see here. Now, in terms of resolution, I'm going to use, this is where I live, St. John's, Newfoundland, image taken from Google Earth. Now, we go back to this map, the resolution of the data from this global bathymetric data set from satellite altimetry is anywhere between 1 to 4 kilometer resolution. So if we go to a map of St. John's, Newfoundland, and not a map, but a satellite image, and we change that to a 1 kilometer resolution image, this is what St. John's, Newfoundland looks like. And so this is essentially the resolution we have of the ocean floor at a global scale. And that would be equivalent to, if you're thinking about a geological map on land, a 1 to 2 million scale map of the seafloor. So you can see in the bottom right corner, it looks like there's some water, and the top left corner looks like there's some vegetation, and in the middle it's a bit gray. So you could maybe see that there's an urban area here, but that's it. So this is sort of the resolution we're working with at the seafloor at a global scale. And you can see this if you go to Google Earth, they have that data set as a sort of the background map. And so that's what you see here. And you can, if you look closely on this image, you can see all these straight lines on the seafloor, and they seem to be sort of radiating in many cases out of that's Tahiti. And you can zoom in. First thing you don't want to do is Google this, because you'll get about 1,000 websites talking about how this is evidence of aliens creating highways on the seafloor, and all sorts of great conspiracy theories. But if you look closely, you can see those lines represent areas where we have higher resolution bathymetric data. So it's sort of fuzzy in areas, and you can see these lines where there's much higher resolution detailed imagery of the seafloor. And these are areas that have been mapped to a higher resolution using sonar. And in particular, a system we call multi-beam sonar, multi-beam echo sounders, mounted on the bottom of ships, and it pings off the seafloor. And from the timing, you get a much higher resolution map of the seafloor underneath your vessel, up to depending on depth. But I mean, these things could fan out to up to 8 kilometers or so for a swath. And the nice thing about these data is that they're much higher resolution, anywhere 100 to 15 meters at times. It depends on your depth. But here's another image showing a comparison of the satellite altimetry data, which is sort of the fuzzy data, and the much higher resolution, 50 meter in this case, swaths where a ship has gone through and mapped the seafloor to a higher resolution. So okay, we could get much higher resolution maps of the seafloor. Here's a map of the publicly available high resolution multi-beam mapping coverage at a global scale. So anything that's not shaded is where we have bathymetric data at a resolution higher than 100 meters, and everywhere else is sort of that's 1 to 4 kilometer resolution. And there's a push, there's a project called Seabed 2030 to get the entire ocean mapped at 100-meter resolution or greater by the year 2030. We're about a quarter of the way there and quickly running out of time. But that's the goal. Okay, so if we go back to St. John's, and here's our satellite image, and here's our 1 kilometer resolution we could get from satellites. we map this area with a ship and we can get 50-meter resolution. So now we're at sort of a 1 to 100, yeah, that's right, 1 to 100,000 scale map of the seafloor, and this would be the equivalent in terms of satellite imagery. So suddenly you get a lot more detail. You could start, yeah, there's a harbor, there's some lakes, there's some forest area, there's some urban area. You could get a lot more resolution, a lot more data from that. Now, can we do better than that? We can. We can use autonomous underwater vehicles, AUVs. These are essentially underwater drones. They look like torpedoes, but they don't explode. Well, hopefully they don't explode. You could put a multi-beam system on a AUV, just like you can on a ship. But because this multi-beam system is now much closer to the seafloor, you can get a much higher resolution map, albeit over a much smaller area. So to give you a comparison, here's a sort of oblique image of the seafloor. This is an area, if you see that inset map, again off the west coast of North America. There's a can you guys see my my cursor here? Well, I can turn on my laser pointer. Pointer options. There we go. So there's a mid-ocean ridge here. And mid-ocean ridge, usually there's what we call an axial valley running along the length of that ridge. And we have that right here at a site called the Endeavour Vent Field. And so what we're looking at here is we're looking along this axial valley. It's about 1 kilometer across in terms of scale, and it was mapped with a ship at 50-meter resolution. And then we came back, a group from the Monterey Bay Aquarium Research Institute mapped this valley with an AUV and was able to produce a map at 1 meter resolution. So that's what this same valley looks like at 1 meter resolution compared to 50-meter resolution. So you can see obviously quite a difference there. What we're looking at in front of us here, all of these spires and pinnacles here, these are all massive sulfide deposits. This is the main Endeavour Vent Field. These edifices are about 30, 40 meters across and anywhere from 10 to 20, 25 meters tall. So we can image these if we have high enough resolution data. So if we go back to our analogy from St. John's, Newfoundland, we'll zoom in on here's Memorial University. And this is what Memorial University looks like at 1 kilometer resolution. It's a single pixel. 50-meter resolution, and then less than 1 meter resolution, we can discern all sorts of things. At the seafloor, that means we can actually see things like hydrothermal vents. Can we do better than 1 meter or so resolution? We can, but only recently. We have a project last year, and we're still working on this using a new technology called interferometric synthetic aperture sonar. And what this is it's a sonar system like multi-beam. Here's the instrument. This is a remotely operated vehicle here. And right here is essentially an underwater microphone and speaker system. And the way this works is you shoot the sound out sideways when flying quite close to the seafloor, and the sound will bounce off any objects on the seafloor, and we listen to the return. And there's a series of essentially microphones that pick up the sound, and using interferometry and this technology similar to synthetic aperture radar, which is where it comes from, we can produce what we're looking at here is an acoustic image of the seafloor. So this is taking pictures of the seafloor with sound. Light doesn't travel through water at all. It's terrible. We can't see anything at the bottom of the ocean, but sound travels very well. So now we can get images at, this is 3 centimeter resolution image showing ripples in sand and a fractured rock outcrop. Now this technology was designed initially for defense purposes, But more recently, it's being applied to things like offshore archaeology. So here's a shipwreck that's been imaged using synthetic aperture sonar. And then offshore energy infrastructure, so oil and gas, wind, pipelines. You can image all of these sorts of things using the synthetic aperture sonar. It hasn't really been tested out very much for scientific, environmental, seafloor classification, habitat mapping, these sorts of purposes. So this is one of the things we're trying to do right now. We collected some data from near the Galapagos recently. And so here's footage of the seafloor, and this is along a mid-ocean ridge. So there's some ropey lava flows and some sheet flows, and that's what the acoustic imagery looks like on the seafloor. Here's another example. These are pillow basalts on the seafloor. Most mid-ocean ridges, it's just thousands and thousands and thousands of square kilometers of pillow basalts. So we can actually image not just pillow basalt fields, but individual pillows. We can see fractures. We can see different flow morphologies, all from taking these acoustic images. So we're now at sort of the limits of our mapping resolution, in this case, 3 centimeters. One really cool thing we discovered is here's another image of pillow basalts from the Galapagos region. But you see these shadows here. So these are spires. These are black smoker spires. So not only can we image these spires and actually you can measure their heights from the length of the shadows. But if you can see, there's this sort of distortion in the imagery behind. So the illumination is coming from the left of the screens. That's where the sound is coming from. So it's shooting off to the right. The scale here is about 50 meters from top to bottom. And this distortion we see essentially behind these chimneys is from the hot fluids emanating from these chimneys, which distort the thermal properties of water, and therefore the image we can create from that. But with this technology, we can now not only find black smokers, but we can figure out which ones are active and which ones are not, which is pretty cool. Okay, now we run into the problem where you get the higher resolution, smaller coverage area. Low resolution, greater coverage area. You don't get anything for free. So what does that look like? How much can we do with all of these different types of mapping of the seafloor? I'll sort of tell you a bit of a story here. So here we are in the Atlantic Ocean. You can clearly see the Mid-Atlantic Ridge, and there's a little area that is colored here. This is where the TAG hydrothermal vent field is. This is the first vent field discovered in the Atlantic. We had a research cruise to this site in 2016, and it was a 7-week research cruise on the Meteor, which is a German research vessel. And we started in Barbados, and it took about 6 days of driving in a straight line just to get to our working area. And this expedition ended in the Azores, which is up here. So that's another 6 days or so. So out of about a 7-week cruise, we've already lost 12 days just driving. And so we're now down to sort of 4.5 weeks or so in our working area. In this little colored area is what we were able to map with the ship. It wasn't the only thing we were doing during this expedition, but we were doing a lot of different things. But in terms of time we had to map the seafloor with the ship, that's the area that we covered during this 7-week cruise. And we zoom in, we had an AUV with us. And that little tiny area, you can see the outline of the ship map. And that little tiny area is what we mapped with the AUV. Over about 10 AUV dives in 2 weeks. That little square is about 10 kilometers by 10 kilometers. And so that map we have at about 1 meter resolution, and then this greater map we have at, I think it's either 30 or 40 meter resolution. So you zoom back out, and what you realize is that it's a really, 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 really big ocean. And in 7 weeks, total cost of this expedition would probably be several $1 million. Here's the little area that we mapped with the ship at 25, 30, 40 meter resolution. And the size of the area that we mapped with the AUV at about 1 meter resolution is about a pixel on your screen. So that's the challenge we face in terms of exploring the seafloor. Okay, so we go back to our map with our distribution of vent fields, and again, over 400. Now, how did we find all of these? Well, did we find these with these high resolution maps? No, in fact, very few were found that way. Almost all of the sites you see on this map here were found by detecting the hydrothermal plume. So all of these active vent fields are giving off these high temperature black smoke or plumes. These are essentially thermal and chemical anomalies in the ocean. And it turns out that we can detect a hydrothermal plume several kilometers away from the source. You know, a vent field might be a few hundred kilometers in terms of dimensions, but the plume, sorry, a few hundred meters dimensions, but the plume can be spread over several kilometers. So if you can detect the plume, it makes it a lot easier to narrow in, zero in on the location of the vent field. So on the right here, we how do we detect the plume is we use a device called a CTD. CTD stands for conductance, temperature, depth. So it measures salinity, it measures temperature. We could put other sensors on there, methane sensors, redox sensors. And you can lower it on a cable from a ship on a device like this. And these are Niskin bottles, so you could sample seawater at different depths as well. Or you could put these sensors on an AUV. And on the left here, we have an example from some work we did on the southern mid-Atlantic ridge. So here is some ship bathymetry, and this is the ridge axis. And we noticed there's an axial volcano here, and this volcano had been rifted. You can see all these rift faults running through it. So again, we have the two ingredients we need for a hydrothermal system. We have heat, or the volcano there, and we have permeability because we have these rifts. And this is a survey pattern from an AUV. And here in that survey pattern, you can see we had an EH sensor, temperature sensor. We detected essentially two locations where we had hydrothermal venting. So we can then narrow in on that site and then dive down. I'll give you one other example. Here we are, the Galapagos Spreading Center. So here is Central America. There's Ecuador here, Colombia. This is just an amazingly fascinating part of the world. You have the East Pacific Rise, which is a mid-ocean ridge over here. Propagating out of that, you have the Galapagos Spreading Center, so another mid-ocean ridge that's essentially unzipping itself as it propagates next to the East Pacific Rise. You have all of this being subducted underneath Central and South America. And just to add to some excitement, you have a hot spot here, which is why the Galapagos Islands are. So it's just an orgy of geology all in one place. It's amazing. And we went out there last year on the Falkor 2, which is a private research vessel owned by the Schmidt Ocean Institute. Eric and Wendy Schmidt. Eric Schmidt, you might know that name. He's the former CEO of Google. And when he retired with his billions of dollars, you can ask him to use his ship for a while. And so we did that to study distribution of hydrothermal venting along this area. And I'm going to focus in on this little bend right here. So you have the Western Galapagos Spreading Center here, and then the Eastern Galapagos Spreading Center, and then a bit of a transform right there. And so here's that bend in the transform. There's a bit of a bend. So here's the mid-ocean ridge. And then these are two calderas, and they're called the Los Huelos calderas. Los Huelos is Spanish for footprints, because they look like footprints. So there's Los Huelos West, Los Huelos East. And about a decade ago, there's a couple of transects done by Ed Baker and his colleagues with CTDs looking for plumes. So they did one across this volcano, another one across this volcano. Here are the profiles. This is a measure of essentially how cloudy the water is, which relates to, again, a hydrothermal plume. Then up here we have our EH anomalies. So in both of these volcanoes, there was evidence that there was hydrothermal venting. But they didn't have toys to go down and map and explore. They just had the CTDs with them. And so for, what is that, 14, 16 years, we knew there were plumes there, but didn't know anything else, didn't know where they were coming from. So we were driving over this area as we were doing work in there, and we thought we'd stop and take a look. And so we're going to zoom in on this area right here on the eastern caldera. And so we mapped it with the ship at about 15-meter resolution, which is very good. And then we actually put a multi-beam system on the ROV. We didn't have an AUV for this project, unfortunately, but we stuck one on the remotely operated vehicle and drove that around and produced a 1-meter resolution map of this area. So again, you can see 15-meter to 1 meter. You can see the increase in detail there. Now, we've right away focused in on this area right here. Why? Well, we have caldera ring faults right here equals permeability. Again, here. And then this is the rift coming through here, and you can see the faulting from the rift. So we have intersection of two different sets of faulting, and this whole thing being a volcano, heat. So again, all the ingredients to find a hydrothermal system. Went down, mapped it, and I'm going to zoom in right on this area. And I changed the color ramp here to emphasize this right here. You see there's these features that jump out at us because they have the right sort of shape, size, dimensions of black smokers. And so what did we do? Went down. Oh, here's a sort of a 3D of what that looks like. So there's no vertical exaggeration here. This is what the seafloor looks like. And it's all of these features on the seafloor. They're about 10 meters high or so. You can clearly see this caldera ring fault, and you can see the faulting and the rifting associated with the mid-ocean ridge. And lo and behold, we drive up and here it is. We found a brand new vent field. This is we named it the Tortugas vent field after the famous turtles in Galapagos. Okay, so we now know how we can find hydrothermal vents on the seafloor. How am I doing for time here? It is okay. I think we're doing okay. We're getting close to the end. Okay, right now, the thing is because we're finding all of these hydrothermal vent fields, mostly because of the plume. We detect the plume, and then we can go in and map, and then we know exactly where to go. We're missing one critical piece of the puzzle. And what that piece of the puzzle is that vent fields don't last forever. Well, the hydrothermal circulation doesn't last forever. It turns off eventually. So you end up with essentially a dead, extinct vent field. So here's some footage of what that looks like. You don't see the animals anymore. They need that fluid to live. So there's no more animals that are directly related to venting. You get different animals now. You get things like corals and sponges and whatever the heck that thing is. You don't get the chimneys anymore. They all sort of fall over after a while. It's basically massive sulfide that is rusting away. You're forming a gossan on the seafloor, essentially. Now, this is really important for a number of reasons. Biggest reason is if we start talking about seafloor mining, no one really wants to mine the active vent fields because obviously the ecological destruction would be immense. Two, there's a good chance you would destroy your mining equipment if you're trying to mine something and there's 400-degree acid fluid coming out and eating up your machinery. So the idea is that, well, maybe we could mine the inactive vents. Problem is we don't know how to find these. Very difficult to find these because they don't have the plume. So we could rely on high resolution mapping, but as we already saw, it's a very, 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 very big ocean. Makes that very difficult. As a geologist, it pains me to say that geophysical techniques are probably what will be most effective for finding these on the seafloor. And there are a lot of people who are actively looking into how to do that. But when you go back to our map here, we don't know what's the ratio of active to inactive vent fields. We think there's a lot of inactive vent fields, but we don't know. We just we really don't know, which makes it very difficult to assess the sort of the resource prospectivity of this type of deposit when we don't really know how to find these deposits. So that's the challenge that faces us in the future. Once we find whether it's active or inactive, okay, we could use all these remote sensing techniques to map and find these things, but eventually we have to go down there and look at them and sample them. Well, how do we do that? This is the famous Alvin submersible operated by the Woods Hole Oceanographic Institute in the United States. There are a few of these around. The Japanese have one called Shinkai. The Chinese have one. The French, the Russians, I don't think the Russians use theirs anymore. So there's a few deep sea submersibles that you can use to go down, but more often than not, we're using remotely operated vehicles. So this is Sebastian, remotely operated vehicle, ROV, owned by the Schmidt Ocean Institute. Cheaper to run than a human-occupied vehicle, obviously much, much safer. They have, as you can see, lights on them. Here's sort of close-up of the front of it. So, there's a whole bank of lights. There's sonar systems, high-resolution cameras. There's 2 robotic arms, so you could pick up animals, you can pick up rocks, and there's all sorts of buckets and places to put samples and bringing up to the surface. So it's remotely operated. There's no one in there. On the Falkor 2, so the Schmidt Ocean Institute vessel, this is what the control room looks like. So this is sort of a mission control, so to speak, where all the action takes place. We've done work on icebreakers, and you don't launch the ROV over the side in this case. This is the Crown Prince Haakon. It's a Norwegian science icebreaker. We're about 400 kilometers from the North Pole here, and we actually launched the ROV through a moon pool so that it's not doesn't get destroyed by the ice surrounding the vessel. So you go down and you drive around and you can video and you can collect samples. Here's a video image. Now this video has been sped up 4 times just to give you a sense of how difficult it is to pick up a rock from the bottom of the ocean. So here we are trying to sample. This is a black smoker at a site called Niua. It's near Tonga and Fiji. This vent is super cool because if you look closely, this is a boiling vent. So you can see a bit of a white, hold on, can I restart this? Oh, I don't want to screw this up. Oh, it's worth it. Hold on, let's go back. Right, you see all that white there, that's vapor that is condensing. It's essentially flashing right at the surface. So these are fluids that are right on the liquid vapor boiling curve for seawater. We're at about 1,100 meters depth here, so this fluid is about 325-ish degrees Celsius. This is a fascinating vent. Amy Gartman at the United States Geological Survey did a bunch of work on this, and because we found out there's a ton of gold in this vent, and she figured out that it had to do with colloidal gold transport. So wrote a few papers on that. Anyway, we finally picked up a sample. So that was what, a 2-minute video, so time sort of 8 minutes to pick up one sample. And there's your prize. So that's all chalcopyrite and hydrite from the interior of this chimney. This is what the inside of most high temperature chimneys look like. So if you're into sparkly things like I am, then this is the field for you. This chimney was so awesome that it got us the cover of Geology in geez, what year was this? 2000? Does it say on there? I can't tell. 2018. Great article. I highly recommend you all go read it. The gold concentration in this chimney was about 50 grams. Yeah. Okay, this is what sampling a rock from the seafloor looks like in real time, not sped up. And I'm not going to bore you with this, but as you can see, there's a real art to controlling these robotic arms. You have no depth perception because you're looking at a video screen. Often you try to pick up a rock, and these things can be incredibly friable, so the whole thing just disintegrates into a cloudy mess. Can I fast forward? I can't fast forward. Anyway, well, you get the idea. It's a very difficult, time-consuming thing. And we can also collect fluid. So here we are. This is a site called Loki's Castle, which is in the Norwegian and Greenland Sea, so north of Iceland. This is really cool. These are flanges. So you're looking at an inverted pool of hot hydrothermal fluid that collects underneath these sort of protruding, well, what we call flanges. And so what we're holding with the robotic arm here is an IGT, an isobaric gas tight sampler. This one belongs to Owen Reeves at the University of Bergen. And so it has a nozzle, and we could stick it right into the fluid, or you could stick it down into a chimney in sort of a normal circumstance. I'm just showing this because it's cool. But you can collect the fluid, and the key thing is that you can bring this instrument back up to the surface, maintaining the pressure at which the fluid collected. Because if you don't do that, then all your gases, your dissolved gases in that fluid will exsolve as you return to lower pressures at the surface. So we collect rocks, we collect fluids, and we put all this together and tell a story about hydrothermal systems. To get into all of those details would require another couple hours. So we'll leave it at that for now. But you know, finding the vent field is certainly the hardest part. And then the second hardest part is getting samples from the vent field back to your labs. And then that's where the fun really begins. So I will tentatively end here. I'll explain why I say tentative in a second, by saying that, you know, we've, 400 sites discovered on the seafloor. We, the community, black smokers were discovered in the late 70s, so recently. Obviously the community has gotten very good at finding these on the seafloor. But I can't overemphasize enough that we still haven't come close to finding everything that's out there, not by a long shot. And there's so much variability amongst all of these sites, even along the same ridges. Each ridge has its own flavor. All the different tectonic settings have their own flavor, but even along a single ridge, there's a lot of variability. So there's still so much to learn. It's going to keep us busy for quite a while. Now, I'm going to stop there. I did have a few more slides about sort of resource mining kind of stuff. But I thought maybe it'd be best to stop here. If there's people are dying to learn more, we can go through a couple more slides, but maybe we could stop for questions for now. So I'll pass it back over to you, Jessica. And thank
Thank
you
you.
everyone for listening, and I'd be happy to take any questions.
Thank you so, so much. All the footage that you have, that was just incredible. Like being able to see that. Yeah, I loved it. So thank you so much.